All right, let's look at u substitution. The last method we're going to look at for integrating, at least in this review. U substitution is the reverse of the chain rule. So it deals with composite functions, functions that have been plugged in to other functions. If we look at the derivative of a chain rule, the end result, it's complex. It's got g prime and it's got f prime with the original form of g plugged into that. So it can be hard to recognize u substitution, but it is the most common method of integration, really, besides reverse power rule. So if reverse power rule is not going to work, your next choice is probably going to be u substitution. But here it is. If you have the integral of a function with something plugged into it, and you also see the derivative of that interior function kind of floating around in the integral, you're going to use u substitution. You're going to let u be that interior or that plugged in expression, and then you're going to find its derivative du, which will be g prime and dx. Sometimes we have to do a little bit of multiplication to get there, but that's the basics of it. And then I can rewrite my integral as a simplified integral in terms of u, using the u to replace the interior expression as a variable and the derivative to replace all the other stuff in the expression, kind of pack it all into du. And then we just take the integral of the simpler expression. So as an example down here, I have 15x squared times the sine of 5x to the third dx. So clearly, reverse power rule is not going to work on this. But I see my function sine with this 5x to the third plugged in. Sine normally is just sine x. So if I've got something inside of that sine function, I know it's going to be u substitution. I've got to get that out of there. So sine 5x to the third, and then on the outside, 15x squared, which is the derivative of 5x to the third. So this one's set up very nicely for u substitution. I go ahead and let u equal that 5x to the third that I found inside my trig function. Its derivative is 15x squared dx. So just like with the implicit differentiation, when we took the derivative of y, we got y prime. Or if we took the derivative, let's say y squared, you would end up with 2y, and then you would tack on y prime. Same thing here. If I'm taking the derivative of u, then when I take the derivative of x to the third, I would get 3x squared x prime, which is dx. But I take these expressions now, and I rewrite my integral. So sine of u, to represent that sine of 5x to the third that we had here. And then, like I said, everything else is kind of packed into that du, the 15x squared and the dx that we found in the original expression. Then, this is one of those common integrals. I can integrate that. The integral of sine is negative cosine of u plus c. My last step, since my original integral was in terms of x, I want to finish in terms of x, so I undo the substitution and replace u with that 5x cubed that we had, and there you go. That's your integral. So that's u substitution, method-wise. Now again, I'm just going to work through a couple of the examples in the Khan Academy problem sets that this goes with. Let's start there. Here we have u substitution. Definite integrals, we don't want that one. We want defining u. That's where we start. U substitution, defining u. In these problems, it's really just going to ask you, hey, what should u be? How would you choose u given this integral? So let's look at those. Here. Gotta use the right mouse. Anoop was asked to find the integral of the natural log of x to the 8th power using u substitution. What should u be? Well, again, remember, u is the interior expression. It's the thing that's been plugged in. You're trying to take out that interior, because it's making it more complex, and replace it with just a variable letter u. So in this case, it's that natural log of x that I see being plugged into that power function. And I know that's going to work because I'm thinking, well, what's the derivative of the natural log of x? The derivative of the natural log is 1 over x dx, which I could use to replace that x and that dx in terms of just du. So I get u to the 8th du. Much easier, much simpler to integrate. So in this case, hey, all I had to do is, how should he define u? What should u be if we want to use u substitution to do this problem? And again, the rest of them very similar to that. For this one, the parts of the integral is I have a 6x squared out here, cosine 2x to the third plus 1. Well, again, that's really the only thing being plugged into some algebraic form. So that 2x to the third plus 1 is going to be u, or at least I think it's going to be u. That would allow me to write this as just cosine of u, much simpler. But if it's going to work, I need its derivative to also kind of be floating around on the outside of that function. In this case, du would be 6x squared dx, which would work very nicely, 6x squared dx. So u is that interior expression, in this case 2x cubed plus 1. So that's all you're doing on the first exercise, that defining u, just kind of figuring out, well, how do I choose a value for u? Then indefinite integral. So this is really just finding u and then going ahead and doing the integral. So let's look at a couple of these. All right. So it's probably one of these 4 answers, but we've got to figure it out. So we've got x squared over x to the third plus 4 dx. There's a fraction. A rational function, I should say, instead of fraction. Let's use a bigger word. Rational function. Rational functions, 1 over x. So if we have a fractional form, it's probably the denominator that's being plugged in. Now, not always, but in this particular case, it is. So I'm going to say, well, what if I let u equal that denominator, x to the third plus 4? Then I could rewrite the whole thing as just x over u, or 1 over u, even better. That nice, easy, rational form. So let's see what we can take care of with the derivative. That would be 3x squared dx, which is kind of good, but we don't have 3x squared. We just have 1x squared. But I can deal with that by dividing the whole thing by 3, so 1/3 du. Now my integral would be the integral of 1 over u times 1/3 du. Again, that constant, if I ever have to multiply du by a constant, it's really just going to go on the outside of the integral. I just wrote it like this to show you, but it's going to be 1/3 the integral of 1 over u du. And that's a common integral. We know the integral of 1 over u is the natural log of u, so now we have 1/3 the natural log of the absolute value of u plus c. But if I look at my options, all of these are back in terms of x. So I need to undo that substitution to get my final answer, which would be 1/3 the natural log of the absolute value, and then of the x to the third plus 4. That original expression that I used u to replace. So we just need to find that one. 1/3 the natural log of x to the third plus 4 plus c, and that one matches a. Here, I think they integrated, so they added 1 divided by, yeah, they integrated this. That's not going to work. You can't integrate the interior expression. This one, it's a little bit like chain rule, multiplying by that out there, but again, that doesn't work. It's A. Follow the u substitution. Again, here, I'm definitely not going to be able to use the reverse power rule on this. There's just too much going on in the expression. So u substitution is going to be a better method. I see I have 5 plus 2x squared. The derivative of that would be 4x, which is kind of what I have on the outside, at least in terms of my variables. Then constants don't really matter. 4x, 27x, and 1/3 x, they're all basically the same derivative. It's linear. So here, u is going to be 5 plus 2x squared. Du, we've already said, is going to be 4x dx. And then, since I only have the x on the outside here, I need to get rid of the 4, so it's really just going to be 1/4 du. So I can write my integral. It's 1/4 the integral. The x and the dx are going to be covered by du, so it's the square root of u du. Now, that is equivalent to the original expression. All I've done is said, look, I don't want to look at 5 plus 2x squared in this integral, so I'm going to replace it with u, and since I'm changing the variable, I have to change that dx to du, so I have to find something to replace that. That's what we did. So we just rewrote the integral in a nicer form, kind of like when you're cleaning your room and you tuck a lot of toys under your bed, you know, so your wife doesn't see them. Maybe you bought some more Star Wars Legos, trying to hide those again. But so we rewrite them in this u form, hiding the complexity under the bed that is our variable u. Now we can integrate this. That's just the power rule. I know the integral of this square root is 1/2 square root of u. We'd have that constant on the outside. So we would end up with 1/8 the square root of u plus c. And then undoing that u would be 1/8 the square root of 5 plus 2x squared. And then I'll go ahead and add my plus c here, even though they have it already there. Now we just have to enter that in. It's going to require a fraction. 1/8, and then our square root of 5 plus 2x squared. And that would be our answer. Plus c. Check again. All right. Let's see. Chances are it's just the way I entered it. But, yeah. Yeah. Did that. We got that. Good. All right. And again, if you get an answer wrong, it'll ask you, watch a video, get some help. Do that. I mean, it's kind of the idea. It's the same as in class. If you were struggling on a problem and the next day I said, any question in the homework, and that was your question, you would ask me that question and get the help. That's all we're looking for here. So again, we got this. That's what I did. That was a silly mistake. I differentiated. The derivative of the square root of u is 1 over 2 root u. But we're not taking the derivative, are we? We are taking the integral, which means I need to add 1 to the power and then divide. So 1/2 plus 1 would be the 3/2 that you see here. All right. That makes more sense. So again, and they got, that's right, 2/3 u to the 3/2 power. Again, simple mistake. We have derivatives and integrals. Sometimes we get confused, especially with u substitution, where the first step is really to differentiate and the second step is to integrate. I differentiated my square root relatively confidently to get that correctly incorrect. That's how you do it, but I was wrong. So I go back, check that mistake. Got to integrate in the integral using reverse power rule to get that, which is going to change the rest of this. So again, now that I've identified my mistake, I can go back and fix that. It's 2/12, so 1/6 u to the 3/2 power, which would be 1 over 6 times that 5 plus 2x squared to the 3/2 power. And then, well, let's see if we can enter this in. So let's get rid of this incorrect answer. Try that. I'm going to do it, still need the fraction. On the top, I'm going to put this into radical form, because that's what we started with. So 5 plus 2x squared, 5 plus 2x squared. And then I'm going to raise that to the 3rd power. Can you do that? No, it doesn't like that. All right, let's do it. As parentheses, and then to the 3rd power there. And then the whole thing should be over 6. Does it like that answer? Let's see. Yeah. Okay. I think it would have taken the rational exponent form as well, but chances are that. Now again, if it wouldn't take this, even though it's equivalent, it would mark it wrong, and I'd have to go through the hints and see, okay, well, what happened there? Let's see if I can still do that. So I marked it wrong, so I go get another hint. And we can see that's the answer it gives us there. 1/6, 5 plus 2x squared to the 3/2 power. Okay, so that matches our expression. And that's exactly, so they didn't actually bother putting it in that way. They just left it in the rational exponent form. All right. So that's fun. Nice embarrassing mistake there, differentiating when I should have integrated, but easily correctable. The only other exercise with this is definite integrals, which is exactly what you do here. And then once you've got it back in terms of the original variable, you would do f at b minus f at a, just like we've done with all the other ones. So good luck on that one. I'll do one more on separable differential equations. They work basically how they sound. You're going to separate the variables and integrate, but I'll show you that video. And then that's it. There will be another test posted to Google Classroom tomorrow. And I'll be sending out emails for those of you who haven't taken the test yet. Make sure you get that done. But other than that, all the work is there. Everything should be posted and ready for you guys to complete by the 15th. So you'll have a whole week for seniors, 2 weeks for everybody else, just to get that done and caught. All right. See you next time, guys.